Okay, now that we've talked about all the fundamental rules of probability, now we can actually apply those rules. Okay, this whole chapter is on what's called discrete probability distributions, and the next chapter will be all about continuous probability distributions. Okay, so the objectives here are to distinguish between discrete and continuous random variables. We'll talk about what a random variable is. Identify discrete probability distributions, construct probability histograms, compute, interpret the mean of a discrete random variable, and then also the standard deviation of a discrete random variable. All right, so let's start off with just defining what a random variable is. Okay, so a random variable is a numerical measure of the outcome of a probability experiment, which we've talked about before, or a random process, so its value is determined by chance. Random variables are denoted by using an uppercase letter such as x, where the list of the values are ran with the lowercase x. All right, so as we discussed in the probability chapter, a probability experiment could be as simple as rolling a die, right? A probability experiment is essentially something that's a repeatable process where the outcomes are uncertain. Okay, so for example, rolling a die, there's 6 outcomes, and there's actually a probability for each one of those outcomes. Okay, so that's what we mean by a random variable. Okay. All right, so there are 2 types of random variable. Those are discrete and continuous, as far as numerical random variables. So the discrete random variable is a random variable that has either a finite or a countable number of values. Okay, so for example, such as 0 through 4 in this case, all the countable numbers. And as you see, we have just the solid values right here. These are just the integers from 0 to 4. Okay, and they're countable. There's 5 outcomes in that case. Continuous random variables has infinitely many values and that are not countable. So these are usually come from things that are being measured. For example, like the height of the average student at the school. Okay, that is something that's being measured. Technically, there are an infinite amount of heights. Every particular person has a unique height. We just round to the nearest inch or centimeter or whatever. So we have a bunch of unique little values, actually infinitely many, because between any 2 numbers, you can always split the difference between any 2 numbers, and you can keep on doing that infinitely many times. So there's an infinite amount of numbers between any 2 numbers, really. Okay, so this chapter is all about discrete random variables. All right, so let's just determine whether the following random variables are considered discrete or continuous. And for the most part, it does require a little bit of common sense and intuition to answer these. So example 1, toss 4 coins and count the number of heads. Well, first of all, are these discrete or continuous? And since we are counting the number of heads, I would say that's discrete. And if we can list out the possible number of heads in 4 flips of a coin, well, in 4 flips of a coin, can you have 0 heads? Well, yeah, you can have 0 heads, and that means everything else was, the 4 coins were all tails, right? So you can have 0. You can have 1 head, 2 heads, 3 heads, 4 heads. Can you have more than 4? Well, no, because there's only 4 coins, so it's impossible to have anything more than 4 heads, right? So we have 5 outcomes here. Example 2. Consider an experiment that measures the time between arrivals of cars at the drive-thru. Okay, so time, it's being measured, right? So this would be something that's considered to be continuous. Okay. Now for continuous random variables, you can't just list them out like we did for the discrete ones. So instead we just say that this random variable t is greater than 0, right? You can start the clock as soon as one car leaves, it starts at 0, and until the next car leaves, you stop the timer, right? So technically it's greater than 0 all the way on to infinity, really, because who knows, that last car might have been the last customer ever, who knows. So that's what that would be. Example 3. Counting the number of light bulbs that burn out in a room of 10 light bulbs in the next year. Let n be the number of burnt out light bulbs out of 10 in the next year. Okay, so again, we are just counting stuff. So this is just going to be discrete, right? Now, can there be 0 light bulbs that burn out in the next year? Yeah, well, if they're all really good quality light bulbs, they should last a year, right? So there's a good probability that they would all last a year and then none of them will burn out. There's a probability that one of them will burn out. There's a probability that 2 of them will burn out. Of course, if these light bulbs are new, they tend to have a longer lifespan, maybe 10, 15 years. I'm not sure exactly what the number is, but as it would keep on increasing, this the probability of such event will decrease. Okay, so technically you can have all 10 light bulbs burn out, right? But the likelihood of that, especially if they are all independent, which we'll see, is very small. So there's 11 outcomes. Example 4, counting the number of leaves on a randomly selected oak tree. Okay, again, we're counting. So discrete. Let x be the number of leaves on a randomly selected oak tree. So x represents the number of leaves. Well, you can find yourself an oak tree that has no leaves, right? You can find an oak tree that has 1, 2, 3, 4. And really, since there's no indication of there's no maximum value of how many leaves a tree can have, it's not really infinite, right? Physically speaking, it's not really infinite, but it's just there's no upper limit to it. So we just keep on going. I can just go ... It's countable, at least. Okay. Okay, let's talk about a probability distribution. So we did kind of allude to this in the previous chapter, but it's good to go over this one more time. All right, the probability distribution of a discrete random variable x provides all the possible values of x with their corresponding probabilities. A distribution could be in the form of a table, a graph, or some sort of mathematical formula, which we'll see in the next chapter when we start talking about binomial distributions. Example 5. You toss 2 coins and count the number of heads. Let x represent the possible number of heads in 2 flips. Construct the probability distribution for x. Okay, so x is the number of heads in 2 flips. Okay, so in 2 flips of the coin, can you have 0 heads? Well, yeah, that would be a case in which we have 2 tails, right? Can we have 1 head? Yeah. Can we have 2 heads? Yeah, that would be 2 heads from 2 coins. You can't have more than that, right? There's only 2 coins, so you can't have more than 2 heads. All right. So 0 ranges from 0, 1. I'm sorry, x ranges from 0, 1 to 2. And this list is just kind of describing how you can actually achieve these. Well, if we let tails be t and heads be h, then one way to get 0 heads from 2 coins is that they were both tails, right? That's only one way. How can you get 1 head out of 2 coins? Well, the first one could be heads, and the second tails, or the first can be tails and then the second heads. And then finally, how can you get 2 heads? Well, they would both have to be heads. Okay. Now, we do know that coins are independent from each other, right? Again, the result of one value or one coin has no dependency on a previous coin being tossed, right? They are independent events. And the probability of independent events of a tails and a tails was just simply the product of each probability on its own. So the probability of getting a tails would be 1/2. And the probability of getting tails on the second coin would be 1/2, which is 1/4, or in decimal format, 0.25. Now, this next one here, we're saying we can have a heads and a tails, or, comma, or a tails and a head. So I specifically said the word or because we know that in or probabilities we're going to be adding. Okay, so probability of getting a heads and then a tails. Well, the thing about coins is the probability of either getting heads or tails is both 1/2, right? So 1/2, that's the first one, that's heads, tails. And then this whole or business tells us that we're going to add, and then tails and heads, another 1/2 times 1/2. Each one of these is a quarter, right? So we have a quarter plus a quarter, and a quarter plus a quarter, 2 quarters, or 1/2, which now I'm going to go off screen, or off the table, 0.50, right? Okay, and for this last one, heads, heads, that's only one way that can happen, and the probability of getting a heads on each coin. Independent event, 1/2 times 1/2 is 1/4, which is 0.25. And what have we said about the sum of all the probabilities in a probability distribution for discrete random variables? These should add up to be 1. 0.25 plus 0.5 plus 0.25 should be 1. Okay. All right. Now that one was a little bit more simplistic, mainly because it's just a coin, so the probability of each one of those events, heads or tails, is 1/2. We can make it a little bit more complicated later on when we get to the next section, I would say. All right, so the rules for a discrete probability distribution are as follows. There's a numerical random variable x, and its values are associated with the corresponding probabilities, as we saw above there. And probability of x denotes the probability of a random variable x equaling some value x. Okay. All right, so then the sum of all the probabilities, as we see above, should add up to be 1, right, which we got up there. And also each probability must be between 0 and 1 inclusively. Okay, so that's this business, right? None of those probabilities above were less than 0, none of them were negative, or none of them were greater than 1. Okay, so they're all bounded between 0 and 1. All right, let's see these examples down below, and let's just determine if these are considered probability distributions. All right, so the first thing is to see if any one of these violate the rule that it's between 0 and 1. I don't see any violation of that. So the next thing is to see if the sum of each probability is equal to 1. Well, if I add all these up, you can verify this yourself, you're going to get 0.97. So in this case, we do not have a probability distribution. Okay. What about this one? Again, let's verify if any of these probabilities are outside of the bounds of 0 and 1. Well, that one right away. All you got to do is have one that doesn't follow that rule, and it's just not going to be a probability distribution. Doesn't matter if they add up to 1. And then what about this? Okay, there's no violation that I see that's outside the bounds of 0 to 1. And if I actually sum up all these probabilities, I do in fact get 1. So yes, it is a probability distribution. All right. So probability histogram. Well, this is going to be very similar to when we talked about relative frequency histograms. Okay, instead of relative frequencies, we're going to be using probabilities. So, starting with this example, it says, draw a probability histogram for the probability distribution below, which represents the number of movies streamed on Netflix each month. All right, so before we go ahead and just tackle this, let's try to understand what we're talking about here. They're saying the number, so X represents the number of movies streamed per month. Okay, so what we're saying here, and these probabilities could be interpreted as really percentage of subscribers, or when you randomly select a person, the probability that they would see 0 movies is 6%. Okay, can have any one of those interpretations. Okay, so yeah, so in this case, about 6% of subscribers didn't watch any movies at all. Okay, 58 watched exactly 1, 22 watched exactly 2, 10% watched exactly 3, 3% watched exactly 4, and then 1% watched exactly 5. Now, in reality, I'm sure there's people that watch more than that, but I'm guessing if they calculated it and then rounded it to 2 decimal places, it was probably rounded down to 0. So that's my guess. And I'm sure this is not real data, of course. All right, so let's go ahead and construct a histogram. Okay, so we have 6 outcomes here, right? 0 through 5. So we're going to have 6 vertical bars here. Okay. Now, I know 0 technically is right here, but for the sake of this problem, I'm going to define 0 to be right here and then have them equally spaced apart. 1, 2, 3, 4, 5, 6. I can actually define that to be -1 if I really wanted to. Okay. And this vertical axis, these are going to be your x values. Okay. This is what do they say? Number of movies streamed per month. I guess I can label this as number of movies streamed per month. The vertical axis is the probability of each one of these outcomes. All right, so to make good use of our space here, I wouldn't really put 100% up here or 1. I would instead put something like, well, the largest one I see is 0.58. So I would probably use like 0.60. Because I can break that in half to 0.30. And then break it up into tens. So here we go, like 50, 40, 20, 0.20, 0.10. Here would be 0. Those could be like my major axis, right? Just probably darken them up a little bit more. And then our minor axis can be just right below. I'll just break it up into 5s. I won't even label it, just because it'll get way too cluttered. All right. For 0, again, I'm going to make that rectangle where 0 is at the center of that. So 6%, well, here's 5%. I'm just going to kind of eyeball it. I would say somewhere around there. I'll even label it just to be very explicit. For 1, it's 0.58, so that's between 55 and 60, a little bit closer to 60. So I'll say something like, oops, I can do better than that. 3 times the charm. 0.58. 2. 0.22, that's between 0.20 and 0.25, a little bit closer to 0.2. For 3, we have 10%, so that's looks like it's like right there. 4, we have 0.03, so here's 0.05. 0.03 would probably be like right there. A small little sliver. And then 5, 0.01. And I'm not sure why I put in a 6. Yeah, we don't need the 6. Okay. So that is our histogram here. Now, the next question is going to talk about the mean of a random variable. Okay. But before we get into that discussion, if you were to take a wild guess and figure out on average how many movies each subscriber would watch per month, what would be your guess? Okay. Well, you see how these histograms, these rectangles here, they kind of give you some sort of weight, right? And so there's a lot more weight on one movie being watched because 58% of them watched it. Also, the next in line would be 2, right? And if I were to get a good guess, I would say something on average, it would be somewhere around 1, maybe 1.2. I know this kind of pulls it along this way, the 3, 4, 5. So if I were to give it a guess, I would say around 1. Okay, but I'm going to show you actually how to calculate it exactly. All right. All right, to calculate the mean or expected value, which we'll discuss in 1 second, of a discrete random variable, you have to use this formula. Okay, now that looks kind of weird, okay, but I guarantee you've already seen this in one way or another. Okay, recall the weighted mean. And that was what? Well, it was mu equals the sum of x times the weights divided by the sum of the weights. Remember that? Okay. Well, in our case, we're essentially dealing with our x values here, right? And the weights here are essentially the probability. So all those w's, I'm just going to replace with the probability of x. So let's do that. Sum of x times the probability of x over the sum of the probability of x. Now, so far, if you were to compare these two equations to each other, this numerator looks exactly like that. However, we have this denominator down here, the sum of the probability of x. And what do we know about the sum of the probabilities of x? If we were to do that for this particular problem, if I go back up here, these, when you actually add them up, it will actually add up to 1. Always, if it's a probability distribution. Right, so if that's a probability distribution, that'll always equal to 1. So this just comes out to be the sum of x times the probability of x. So it's essentially just the weighted mean. All right, so let's do that for this previous example. And we can do it by hand. And of course, I can show you how to do this using a calculator, like we have done with weighted means in the past. All right, so compute the mean of the probability distribution. All right, so the mean is equal to the sum of each x value times its probability. All right, so let's start with the first row. 0 times 0.06 plus 1 times 0.58 plus 2 times 0.22 plus 3 times 0.10 plus 4 times 0.03, then plus 5 times 0.01. Okay, so I'll do this piece by piece. Well, 0 times anything is 0. 1 times anything is that anything, 0.58. 2 times 0.22 should be 0.44. 3 times 10 cents is 30 cents, right? 4 times 3 cents is 12 cents. 5 pennies is 5 cents. Add those all up. What do we get? 0.58 plus 0.44, 0.3 plus 0.12. You get exactly 1.49. And the units of this, so the units of a mean is always the same units of your x value. So in this case, it's movies. Movies watched. Okay, so on average, there's 1.49 movies watched per month. And that kind of was in line with my suspicion, right? If we look back up here, 1.5 is around here. So I would say, yeah, that seems appropriate there. Also, anytime you hear the word expected value, or what's the expected value, it's the same exact calculation. So typically what we try to do is make some sort of predictions, okay? And what we use for the predictions is the mean, Okay, so anytime you hear the word expected value, it just means the mean. So it's the same calculation. All right. Example 9. A term life insurance policy will pay a beneficiary a certain sum of money upon the death of a policyholder. These policies have premiums that must be paid annually. Okay. Suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. Okay. According to National Vital Statistics Report, the probability a female will survive the year is 0.99791. So a pretty high chance of survival. Okay. That's why they're charging only that much for a potential claim of $250,000, right? As you'll see. Compute the expected value, there's that word, expected value, of this policy to the insurance company. Okay, so to the insurance company. All right, so we're talking about essentially cash flows. And from the perspective of the insurance company, any money that's going towards the insurance company will be considered positive. And any value that's leaving the insurance policy, or any dollar cash flow that's leaving the insurance policy, would be considered negative. Okay? All right, so of course, if you buy a term life insurance, there are only two outcomes at the end of the year, right? You either survive the whole year, right, and you just paid off your premium, right, and you just lose that premium, right? You recovered for a whole year. Or you might die, right? And if you do die, you pay your premium, but your beneficiaries will get that payout. Okay. Now, from the perspective of the insurance company, if you survive the next year, this X will be considered your cash flows. Okay. If you survive the next year, well, the insurance company receives $530, right? And that's really it. Okay. There's no other exchange. Now, if someone dies, well, at the beginning of the year, the insurance company received $530, but upon death, they have to pay out $250,000. So there's a net cash flow of 530 minus 250,000, and it is negative, right? Negative. I'm going to put a dollar sign in front of this. 249,470. Okay, so here's put a little dollar signs in front of everything. Okay, so those are the two outcomes. Either you survive and the insurance company receives $530, or the policyholder dies and they lose out on that much money. Now, what was the probability of survival? Well, we're told that it's 0.99791. And of course, either survival or death, they are complements of each other. So the probability of death would be 1 minus 0.99791, which in this case is if I can fit this in here, so 0.00209. So it's a small chance. Okay, if you're looking at the thousands place, 2 out of 1,000. Okay. All right, so it's asking us to compute the expected value. Okay, the expected value here is, well, the same thing as our mean, which is the sum of x times the probability of x. Now, there's only 2 rows here, so there's only going to be 2 terms, right? We're going to have our first cash flow of 530 times the probability of that, 0.99791, plus the second row, which is a negative 249,470, times the probability of that occurring, which is 0.00209. Okay, if you multiply those, and of course this turns out to be subtraction, you will get the following. A positive number, $7.50, if rounding, I believe. Okay. So what this means is that they priced it in such a way that every time they sell one of these policies, they can expect to make $750 every time they sell one of these policies. Okay, because sometimes, most of the time, they're collecting those $530, right? 99.7% of the time, but only about 0.2% of the time they're actually paying out. Okay, and that seems like a very, very small margin there. But if you were to sell many of these policies, let's say like 1 million, then you can expect in that year to make a $7.5 million profit. Technically, right? They still have to pay out their overhead and all that, all the costs of running business, commissions and all that. So that's probably all built into that number. Okay. All right. All right, no more talking about death. Let's talk about games here. Example 10 says, a roulette wheel consists of green slots, which are numbered 0 and 00, and then 18 black slots, 18 red slots. A dealer rolls a ball around the wheel, and the ball randomly lands on one of the green, black, or red slots. Okay. Now, before we go on, a roulette wheel has a bunch of numbers also, but right now we're just considering there's colored bets, right? They can be either green, red, or black. Okay. That's the type of bet we're making. So as a player, you bet $1 on red. Now, if the dealer does roll a red, okay, you actually win $1 back. Okay, actually, you double your money, essentially. Okay, so you net $1. Otherwise, you lose $1. So if it lands on either green or black, you actually lose that $1 that you betted. Okay, so they're already telling you what the cash flows are. You don't have to do any subtractions. Let W be the amount of your winnings or losses per game. So this is from the perspective of the person, the player, right? Okay. The probability distribution for W is the following. Okay. Now, they say that if it lands on red, you make $1. So you make a profit of $1. Because you make $1, they give you back 2. You bet $1, they give you back 2. So technically you have a net of $1. Otherwise, you just lose that $1, right? So if it lands on green, you're going to lose $1. If it lands on black, you'll also lose $1. Now, we need to come up with the probability of each one of these occurring. Well, let's see here. What did they say? There's 2 green slots. There's 18 black slots. And the reds are also 18. If you were to add these up, there's a total of 38 slots on that wheel. All right. So if there's 2 out of 38, that should be the probability, right? So 2 out of 38. For black, there's 18 out of 38. For red, there's 18 out of 38. All right. And if you were to add these probabilities up, 2 plus 18 is 38. Divided by 38. It does add up to be 1. So this is definitely a probability distribution, of course. Again, the question is find the expected value. So just like we did above, there's 3 rows, so we're going to end up having 3 terms when expanding out this formula. And interpret the value in the context of the problem. All right, so the expected value of, we're not using X, we're actually using W. We decided to change up the variable letter. Is just the mean, right, of the sum of W times the probability of W equals, well, each cash flow times the probability of that cash flow. All right, so we have -1 times 2 out of 38 plus -1 times 18 out of 38 plus a +1 times 18 out of 38. Okay. you could run that through your calculator if you like. But if you notice, the very last two terms are exactly the same, except for one is negative and one is positive, so they cancel out. And we're just left with the following. Negative 1 times 2 divided by 38 is negative 2 over 38. And since we are talking about numbers, I mean dollars, let's go ahead and see what this approximates to. Actually, let me just throw this in my calculator. 2 divided by 38. You get a negative 0. I won't run down to pennies yet, and I know why, because there's this follow-up question down here. So 0.05, let's go with 3. If we round it to 1,000. So about 5 cents. So from the player's perspective, every time they play, they expect to lose 5 cents. Because quite often you are winning. 18 out of 38 times you are winning. But the other, 20 out of 38 times you're going to lose. So on average, you should be around even, right? Now, but if you play this game 1,000 times, then what would be your net amount that you expect to win or lose? Well, 1,000 times this expected value. You can see why I round to the thousandths place, because I just moved the decimal place over 3 times. So this is negative 53. So if you play 1,000 times, on average you expect to lose $53. Okay, so you can just sit there at the roulette table for hours, really, depending on how fast they play each game. And on average, you should expect to pay $53. So you're essentially just paying to occupy your time there. But of course, this is just an average. Sometimes you will win, and sometimes you'll lose. But on average, you will lose. Everything's always in the favor of the house, of course. That's how they say in business. All right, now to find the variance of a random variable, here is a formula. Okay, just like when we're dealing with the variance and the standard deviations of frequency distributions or weighted means, it follows just the same way. Now, what we're going to do in our class is just use our calculators to do this. So for the exact same problem that we just did, it's already filled out here. Let's calculate the standard deviation here. So in the calculator, we're going to use 1 var stats. And if you're using the TI-83, you're going to put in L1 if this is L1, comma L2 if this is L2. And if you have a more modern calculator, it'll actually give you a menu in which you put in your list and your frequency list. Okay. So let's go ahead and switch over to the calculator here. So if I turn on my calculator, clear this out, I'm going to put this first column in L1. So you go to Stat, Edit, clear out all my lists. I don't need any of these. All right. So -1, make sure you're using a negative symbol, not the subtraction symbol. Another -1, +1. On L2, I'm going to just go ahead and put 2 divided by 38. Now, before you press enter, just make sure you type that in, because as soon as I press enter, it'll be hard to tell what that was, because once I hover over that, it just kind of showed me a decimal equivalent. So it's hard to tell what I punched in. So the next one would be 18 out of 38. Yep, I put that in right. The next one's also 18 out of 38. One of the most common mistakes is just to think that you actually punched in the button, but it didn't actually register. It happens to me all the time, so I would always double check your inputs. All right, that looks good. Let's go ahead and jump back out to the home menu, so second quit. And let's go back to stat menu, go to calculate, 1 var stats. L1 is my list, so second 1. L2 is my frequency list. I'm going to go ahead and calculate, and I should get something like, here's my standard deviation. Okay, so 0.99, so standard deviation is 0.999. Yep. And of course that's in dollars. So about $1 is essentially the average deviation from the mean.